Everyone, welcome to my channel. So in this video I'm going to cover the solution to this question, and at the same time I'm going to go through the general steps we should follow in a coding interview when I try to solve this problem. So before we start the real content, I would really appreciate that if you can help subscribe to this channel. So let's take a look at the question first. Given an integer array nums, return the length of the longest strictly increasing subsequence. So a subsequence is a sequence that can be derived from an array by deleting some or no elements without changing the order of the remaining elements. So for example, the 3627 is a subsequence of the array 0316227. So so it's pretty clear, and here are some examples. Let's take a look at the constraints. It says the length of the arrays are anywhere between 1 to 2500, and each number is between minus 10k to positive 10k. So currently it seems like not too much of the room to think about edge case, and I think we should pretty much understand the question. It's pretty straightforward. Let's see the follow-up. It says, could you come up with a n-squared solution? Yeah, the answer is yes. And the other thing is, could you improve it with a n log n time complexity? So it's this is a pretty laxy question, pretty laxy DP question when we try to first learn DP within the textbook. So for the n-squared solution, pretty straightforward. I'll try to cover the n-squared solution, and then the n log n solution, and then I'm going to do some coding work on the n log n solution because it's a bit trickier. So n-squared solution, we just define like a DP array. It's a 1D array. Essentially it has the same length with the nums input array. So the DPI is DPI means length of the longest subsequence that include nums I between 0 to I. So it's essentially something like until nums I, what is the longest subsequence that includes nums I? So it records the length. Then if we try to compute the dpj, we are going to, when computing the dpj, what we are going to do is we are going to go through all the dp0 to dpj minus 1. So suppose, suppose nums k is smaller than nums j, then potentially we could leverage the dpk to compute the dpj. So that is because suppose we have the dpk and we see, okay, the nums k is smaller than nums j, then we can further append another number on top of dpk to get a longer subsequence that satisfies the condition. So in this case, the runtime is going to be n squared because we have like a 2-layer of the for loop, and for the space-wise, it's going to be linear. So this is essentially the n squared solution. So there is a better solution regarding the runtime, which is n log n. So for the n log n solution, pretty standard. So what we are going to do is we are going to have like another DP array. So let's say we just call it, I'll just call it the n's array. So the n's array starting at so first of all, how are we? So first of all, this is a 1D array. So first of all, we are going to initialize the n's array. So at the very beginning, the n's array is empty. So at the very beginning, we are going to initialize it with one number, which is the first number of the input nums array. So we are going to init nums n0 as nums0. And then for the further update, it's something like if let's say if nums I is larger than the last number within an array, within the n's array, then we are just going to append it to n's array. So it is going to grow. Otherwise, if the number is not larger than the last number within the array, then we are going to do a binary search within nums array. Within n's array, to see which part we can potentially update it. So for example, let's say if the n's array is something like 1 and 5 and 7, and we are trying to search, and the current number we are trying to look at is 6, and we see, okay, 6 is definitely no larger than 7, we are going to do a binary search. And when we do the binary search, the number of course is not there, and for the binary search we are going to return the first number that is larger than 6, and here because it's larger and it's the first number larger than that, we are just going to update it with 6, just to replace it with something smaller. So the intuitive here is pretty much just try to put a correct path for the further computation. So it's something like because originally it is 7 and now we update it as 6. So let's say okay, maybe this is maybe I can try to make it a bit better. Let's say originally it is 8 and we are trying to search for 6, and we replace it with 6. And furthermore, let's say there is a number that comes after this which has 7, then we can further extend the array to include the 7 to append it. Otherwise, so for the original case, if it is still 8, then we cannot really append the 7 at the end. So that's the intuitive for this kind of the solution. So for the outlier, we have like a iteration from the beginning to the end of the array, and then within the inner for loop, you are going to do a binary search potentially. So for the binary search, it is going to be login. So that make the algorithm to be a login for the runtime. So having said that, let's do some coding work on top of the login solution. So like we said, we are going to have the list. Let's call it ends as new array list. And then what we are going to do is we are going to append the first number into it. So we are going to, or it's actually add nums0. And then we are going to go through the rest of the number. I is equal to 1 as smaller than nums.length and plus I. So if nums I is larger than the last number, so ends dot get, say ends dot length minus 1. If it is larger than that, then we are just going to add it, and we are just going to append it to the to the ends array. Otherwise, here we're just going to continue. Otherwise, it is smaller or equal, then we are going to do a binary search on top of it. Collections dot binary search for within the ends array for the number which is nums I. So so I would say just the pose. If the pose is a positive number, then it means the number nums I exist in the answer array, then we just don't need to we don't need to update the answer array. Otherwise, if it is smaller, that means the number doesn't exist. Then we are just going to try to update the corresponding place. Like I said, for example, it is 158, and when we try to do binary search for 6, then we are just going to get the position, which is the first place we are going to update within the answer array. So if pose is smaller than 0, then we are just going to have it will be something like ans dot set. This will be pose plus 1 minus pose plus 1, and then an inactive on top of it. We are going to set this place as num sign. And that's pretty much it. And finally, we are just going to return ans.length. So let's depend on this platform to help us do the debugging stuff. Okay, so ans.size. Okay, ans.size, I think. Alright, so now it's accepted. Let's try some other test cases to make sure. Right, so let's do a submission on top of it. Cool, so that's pretty much it for this coding question. So if you have any question about the solution or about this piece of code, feel free to leave some comments below. If you like this video, please help subscribe to the channel. I'll see you next time. Thanks for watching.